All right, hello and welcome to our discussion of waves. So, there are two different kinds of waves that we can have. We can have mechanical waves, which requires a medium to move through, or electromagnetic waves, which does not require a medium. It can travel in a vacuum. So, for example, a mechanical wave is like a surfing wave. This wave is moving through the water. The water is its medium. But light can move through a vacuum. Light does not need a medium to travel through. It can travel through space from the sun to us just fine. So light is an electromagnetic wave. Now, what is a wave? A wave is a disturbance that transfers energy. So whether it's moving through a vacuum or moving through a medium, it is transferring energy from one place to another. In a mechanical wave, which is what we're going to talk about today, the wave travels along its medium, whatever it is, but the individual particles just move up and down. So if I have a rope and I move my hand up and down while holding onto the rope is going to make a kind of sine wave pattern. It will move up and down. Now, the energy in this wave is going to move through the rope as the wave moves along. But the individual particles in this rope aren't going to move side to side at all. They just move up and down, back and forth. Same thing happens in water. So if you throw a rock into a pond and you get ripples, you can actually see the energy from these ripples moving out this way, along the surface of the water. But the individual water molecules themselves only move up and down, out of the water and into the water. They just move up and down. They do not move side to side along the transference of the energy. Now, all types of traveling waves transport some kind of energy. If we study a single wave pulse, which one hump like this is called a pulse, if we study one of these, we can see that the vibration is transmitted through forces in the medium. So the energy is transmitted because the molecules interact with each other and there are actually forces in there that cause them to move. Continuous waves, or having more than one pulse, starts with the vibrations too. But you can get those vibrating in simple harmonic motion. If you do that, that is when you're going to get a wave like this that looks like a sine pattern, which is why we talked about simple harmonic motion in the last video. Now, let's apply some of the terms we learned in the last video to a sine wave to really understand what a wave is doing. The amplitude of the wave, remember, is the maximum displacement. So if we go to equilibrium, it is how far the farthest point goes. So this is the amplitude. You can get it up and you can get it down. Both of those are the amplitude. The wavelength is from one crest to another, or one spot on the wave to another exact spot on the wave. So we typically measure the wavelength from crest to crest, and it has to go down and come back up. So that's a wavelength. We could also measure the wavelength from here to here. Now, the wavelength is not this part from here to here, because at this point, this wave is coming down and hitting equilibrium, and at this point, it's coming up. So that's actually only half of a wavelength. So you need to be careful about making sure you have a full cycle back and forth to get the wavelength. The frequency is how many cycles you can have of your period in 1 second. And the period is how many seconds it takes to do one complete cycle. So if it takes 3 seconds to do this, the period is 3 seconds. The frequency is going to be 1 Mississippi. You get through a third, or 1 over the period, of your cycle. The wave velocity, or how fast your wave is moving this way, along the energy transferring can actually be calculated by taking the wavelength and multiplying it by the frequency. So the wavelength is how long crest to crest is. That's like your distance. And the frequency is how many of those crests can pass in a given second. So it's kind of like time. So the units for this are still the regular units for velocity, meters per second. You just find it a different way. You find it by taking the meters of the wavelength and multiplying by the cycles per second of frequency. Now, when we talk about mechanical waves, there are two types, transverse and longitudinal. Most of the waves that we think of when we hear the term waves are transverse waves. So that means as the energy moves this way, the individual particles just move up and down. They move perpendicular to the direction of the wave. So the particles on this slinky at this exact point are going to go down and they're going to go up and they're not going to go over. But the energy in this wave is going to transfer from left to right. That's a transverse wave. A longitudinal wave is where the energy transfer and the particles move in the same direction. So that's like when you bunch up a slinky on one side and then you let it go and you see it move back and forth. I'll show you a demonstration of this in class because it's kind of hard to picture. But what happens is the energy moves this way and the individual particles in the slinky also move this way. They move back and forth parallel to the direction of travel of the energy. An example of a longitudinal wave is a sound wave. So if you look at this picture of a drum, the way that a drum works is you hit the membrane or you hit the drum head and it moves back and forth. As it bends out, it compresses all of the air around it. Because those air molecules compress, they want to move forward into other air molecules and they keep bumping into each other. And eventually, those air molecules bumping into each other hit your ear, and you have special little things in your ear that pick up, oh, okay, I'm hearing this kind of tone at this frequency, it must be a drum beat. And then that's what you hear in your brain. It's actually really cool. We're going to talk more about sound probably next week, but just remember that sound is a mechanical wave, so it needs a medium, and it's longitudinal. Now, when a wave hits some kind of boundary, either a closed boundary or an open one, it will do something called reflection or transmission. So if you have a wave hitting an obstacle, it will be reflected, like in figure A. We have one single pulse, and it's moving this way, but the rope is tacked down at the end. So that wave cannot continue moving to the right once it gets to that tack. It's stuck. But the energy doesn't just disappear. We know from the law of conservation of energy that it cannot be created or destroyed. So what happens is it is what is called reflected. And it ends up bouncing where that tack is and coming back underneath or opposite where it was before. So coming in, the wave was on top, traveling to the right, and going back, the wave is on bottom, traveling to the left. Now it gets really interesting when you remove that tack and do the same thing. So if the end of the string is open to vibrate however it wants, you will still get a reflected pulse. However, the pulse is going to be on the same side as it was coming in. So in the beginning, your pulse is traveling on top of the rope to the right, and on the way back, it's still on top and to the left. Now, if a wave reaches the end of a medium, but it hits something where it can still vibrate, some of it will be reflected and some of it will be transmitted. And when it is reflected, it will be upright. So if we didn't tack this down solidly, if we put something loose there, then the reflection would be just like if it wasn't tacked down at all. However, you would get some transmission. And transmission means it doesn't bounce back, it keeps going. So a wave encountering a denser medium, something that is more dense, has more mass per volume, will partially be reflected back, but partially be transmitted. So, if we have two ropes and we glue them together, and I have a light rope and a heavy rope, once this wave pulse gets to the heavy rope, part of that energy moves on through the heavier rope, but part of it gets reflected back. The energy gets split. Now, what happens to the wave's frequency as it travels from one medium to another? Well, let's think about this for a second. We know that for a wave, we can calculate the velocity by multiplying the frequency and the wavelength. If a wave slows down when it gets to the denser medium, let's say it gets smaller, goes down, the wavelength gets shorter, which means wavelength also goes down. Now, because the velocity goes down and the wavelength goes down, the frequency is unaffected. So, if your wave is traveling along and it hits a denser medium and it slows down, it is going to compress. It's going to get closer together between crests. The wavelength itself will get shorter. But the frequency, how many of those crests pass a certain point in 1 second, will be exactly the same as it was before. Now, this is all cool and fine, but a sine wave doesn't really accurately show us a picture of what most waves are doing. And because of that, we draw waves by using wavefronts. Now, a wavefront is a curve of whatever medium the wave is moving through. So, if we throw a rock in a pond and it makes ripples in a circle, your wavefronts are going to look something like the first picture. They're going to be curved, and you can imagine them curving all the way around in a giant circle. And they're evenly spaced from each other. If instead of that, you think of a pool and somebody running into the pool on the stairs, the wavefronts are going to be more straight and less curved. And that's what these are going to look like. They're evenly spaced apart, and they are straight. And this shows you the wave fronts. This shows you where the top of the wave is going to be and where the bottom of the wave is going to be, the crest and the trough. Now, in order to know, okay, my wave is moving to the right and not to the left or vice versa, we use rays. And a ray is a line that is perpendicular to the wavefront, and it tells us which way it's moving. So in the first picture, it's pretty obvious that these waves are coming from a source in the center somewhere, so they're moving out this way, and that's how we draw our rays. But in the second picture, it's really not obvious to us which way this wave is traveling. We just know that it's moving either left or right. In order to know which direction it really is traveling in, we add a ray that makes a 90-degree angle with our wavefront, and we add an arrow to tell us which way this wave is moving. So the blue lines are wave fronts, and the red lines are rays. Now, this becomes really helpful when we get into complicated diagrams like this one. So it turns out, anytime you have a wave of any kind, they will reflect off things, and they reflect in a very specific way. They follow something called the law of reflection. And the law of reflection tells us that the angle of incidence equals the angle of reflection. Okay, so what does that mean? I'll simplify it for you. It means angle in equals angle out. So, if I have a wave coming in at 30 degrees to the ground, when it bounces off and reflects, it's going to come out at 30 degrees to the ground. It's going to be exactly the same. And this is where drawing rays gets really helpful. So, in this picture, it might look really complicated. We have a wave here, coming in this way, and our ray tells us so, and we have the reflection of this wave, which is going out this way. Now, all of the blue and green lines are the wavefronts, and they may get kind of confusing. But if we ignore all of that and just look at our rays, we can clearly see that it comes in at a certain angle right here, and it leaves at the very same angle over here. The angle it comes in at is the same as the angle it goes out at. Now, we typically measure the angle from something called the normal, which is this dotted line in the middle. So this angle right here is equal to this angle. But because the ground is flat here, it's the same thing. If this ground were not flat, you would have to measure it from the normal, from that center line. But they will always be equal, those angles will. Now that's reflection. But waves don't always just reflect and then do their own thing. They're going to interfere with each other. And this is called superposition. And superposition tells us that when two waves pass through the same point, or they're moving through the same space, the displacement of that wave is the sum of the individual ones. So, well, what the heck does that mean? Well, what it means is, if we have one upward pulse coming in to the right, and another downward pulse coming in to the left, if they have the same amplitude, when those meet, they're actually going to cancel out in the middle. Let's say this is +5 and this is -5 meters. To find out how large the displacement is going to be when they meet, you just add those numbers together and you get 0. Now, after that split second of them being in the same place, the waves go on their happy, merry little way. The underneath wave is still traveling to the left and still has an amplitude of 5 meters. And the same is true for the one on the top. It's still moving to the right and still has an amplitude of 5 meters. But for that split second when they were in the same spot, they added to 0. Now, they don't always add to 0. Sometimes they add to make something bigger. So, for example, if we have two positive wave pulses on the top, and this is, let's say, +2 and +2, when they come together in the same space, they make one giant peak, which is 2 + 2, which is 4. So this is going to have a displacement of +4. You just add the previous two together. And again, after they're done, they keep going on their happy little way wherever they were going in the first place. So whenever waves add together to make a bigger wave, it's called constructive interference. Think about construction. They're building something up, making it big. Whenever the waves add together to make 0, that is called destructive interference. You can think about tearing a building down and being destructive. It goes to 0. Now, it can be in between those two. So, for example, in part A, these two waves match up perfectly with their peaks. So when they add, they're going to be constructive. They're going to make a much larger wave, one that is twice as big. In the second picture, the peaks line up with the troughs, or the highs line up with the lows. So when these add together, they're going to cancel and make 0. The third picture, we have them slightly shifted. So the peaks of the top are lined up kind of with the middle part a little bit of the second one. And because of that, they're not going to get really large and they're not going to go to 0. They're going to be somewhere in between. They could even add to be pretty much the same as what they were before. And that is called partially destructive. Now, the way that these things add together, especially to make constructive interference, lends itself really well to something called resonance. And resonance is awesome, and we are going to talk about it in class after you watch this video. Now, resonance occurs when we have something called standing waves. And a standing wave is a wave that looks like it's not doing any work. It just is. It's just there. So if I were to take a string and attach it to the wall and shake it up and down, and I shook it in simple harmonic motion so that the time it took for my hand to go up was the same as the time it took for my hand to go down, I would get a standing wave, and it would look something like this. So you can think of a jump rope. A jump rope is a great example of a standing wave. It goes up and it comes down. It goes up and it comes down. Now, you can have many different kinds of standing waves. You can have the kind that looks like a jump rope, like in picture A, or you can have something that's double. Now, this happens if you were to place something right here so that the strings could not move in the middle. This is exactly how a guitar works. If you pluck a guitar string without any fingers on it, it's only fixed at the top where the head is and at the bottom. It can vibrate everywhere in between, and that's what it looks like. But if you put your finger right smack on the middle of that string, the string can't move right here. It's stuck, so it will move like this. If you were to put two fingers on the string, each a third of the way down the string, you would get something that looks like this. Now, the places where the string is not moving, so at the ends here or in the middle, these are called nodes. And that is where the string does not move. It stays in the same place the whole time. The opposite of that is an antinode, and that is at the very maximum amplitude. So that's there, or here, or here. Those are all examples of antinodes. Now, you probably know that as you place your finger on a guitar and make this shorter, you can actually change the pitch of the guitar. And that's how it works. You can get different harmonics, or what they call resonant frequencies, by putting your finger on a very specific place on the guitar. So, if you want the first harmonic, you just want the string to be open and vibrate as it wills. So, you would just pluck the string, and it would go up, and it would go down. And there would be no nodes except at the two ends. That's called the first harmonic. The second harmonic is where you put one node in, and it can vibrate like this. The third harmonic is where you put two nodes in, and it vibrates like this. So the number of the harmonic is equal to the number of antinodes you have. So if you have the third harmonic, you have 1, 2, 3 antinodes. If you have the second harmonic, you have 2 antinodes. And if you have the first harmonic, you have 1 antinode. If you have the sixth harmonic, you would have 6 antinodes, and it would look like this. It would have a hump, 1, 2, 3, 4, 5, 6. It would look like that. Now, we can actually do some calculations with these based on the frequency and the length of the string and their wavelengths. So the wavelengths and the frequencies of these standing waves can be calculated as follows. The wavelength is equal to 2 times the length divided by the harmonic. So, if I were to draw a standing wave that is the first harmonic, or the first fundamental frequency, that would be 2 times the length of the string divided by the number 1, because this is my first frequency. Now this makes sense to me because the wavelength is how far it is from peak to peak. This right here is only half of a wavelength because it goes up and stops. It doesn't go down and come back to complete the whole wavelength. The whole wavelength would be like that. So the wavelength of this is going to be 2 times the length of that string. Now if I have my second frequency that looks like this, this is a whole wavelength. It goes up and down and then comes back to the original spot. So this is one whole wavelength. So what you would do is you would take 2 times the length of the string and divide by 2. So the wavelength in this case is just how long your string is. It's from here to here because this is a full wavelength. So that is how you calculate the wavelength of one of these standing waves. The frequency is related, but it's actually much easier. It turns out if you know the fundamental frequency or the frequency of your first fundamental, you just multiply it by whatever frequency you're on. So let's say this has a frequency of 200 hertz. Now, if I were to ask you, what is the fundamental frequency of this? This has 3 antinodes, 1, 2, 3. So we know this is the third harmonic. So we would take 3 times 200, which is the original one. So this has to have a frequency of 600 hertz. So it's really easy if you know the fundamental. If you don't know the fundamental, you can calculate it using the length of the string and the speed of the wave. So it turns out there are several different equations to calculate for the frequency of this standing wave. One equation is to take the speed of the wave and divide by the wavelength. Another equation is to take the harmonic number, multiply by the speed of the wave, and divide by 2 times the length of the string. And the third one, and the easiest one, is to just multiply what harmonic you have times the fundamental frequency. So if you have a problem that is asking you what is the frequency of this standing wave, you need to really assess what you are given in the problem and figure out which one of these makes the most sense to use given what you know about your standing wave. And the last property so there are 2 more properties of waves that we need to talk about. We know reflection, we know superposition, we know resonance in standing waves, and you're going to see examples of those in class. And the next one is called refraction. Reflection, refraction. So, it turns out that if a wave enters a medium where the speed changes, and remember, way back here, if we get a wave that moves from one medium to another, its wave speed may change depending on how dense the new medium is. If the speed of that wave changes, it will do something called be refracted, which means that its wave fronts will change direction. So, if we have a wave that's coming in from air to water in a certain direction, this is what it looks like. Our wave fronts are in the blue and our ray is in the red. It's moving along our ray, and the wave fronts tell me where the waves are. Now, when those waves hit the water is much denser than air, and they're actually going to bend. They will change direction. So our waves will now move a little bit more horizontally than they were before. And because of that, because our ray has to be perpendicular to our waves, the ray actually bends, and it will change direction. So you may have seen this before if you were drinking some water or soda or something and you had a straw in your drink, and the straw looks kind of weird and disjointed in the liquid. That's because as the light is traveling through the liquid out into the air, it changes mediums. And because it changes mediums, it becomes refracted. We're going to talk more about that later. But you can actually figure out the angle of that refraction, or how far that wave is bent, by using this equation. The sine of the angle of the second wave front, what you have in the water, divided by the angles of the waves above the water, is equal to the speed of the wave after it hits divided by the speed of the wave before it hits. Diffraction. And this one is pretty easy compared to the last ones. All diffraction tells us is that when waves find an obstacle, they will bend around it. So, if you have little ripples in a pond like this, and they hit a rock, they're going to move along the side of that rock. And as they move along the side of that rock, it turns out they will bend a little bit as they get to the back of it. And this is called diffraction. So the amount of diffraction you have depends on the size of the objects compared to the wavelength of your wave. If the object is a lot smaller than your wavelength, the wave is going to be barely affected. So let's say that in a pond you have some ripples and you have a few blades of grass sticking up. This grass is really, really small compared to the wavelength of your waves. So your waves aren't going to bend around them very much. They're not really going to be phased. But if the size of your wave is comparable to the size of your wavelength, the diffraction will be more. So if you have a log that is sitting in that same pond, and it's a pretty big log, this is a good size compared to the wavelength. So as the wavelengths come by, they are going to bend more than they did with the blades of grass. I know that a lot was covered in this video, and we're going to do some labs to get a better feeling of what all of these kinds of things mean. But in the meantime, try and answer these 3 homework questions because they'll really help you get a better understanding of what was talked about in this video. So the first question is, name the 2 types of mechanical waves and give me an example of each. Number 2, define reflection, refraction, diffraction, and resonance. And I know we didn't talk about resonance really that much, but look up an answer and cite your source, or try and guess from what I was talking about with superposition what it might mean. And 3, a wave is 25 meters high and 26 meters long. Assuming that these waves travel at speeds of 6.5 meters per second, determine the frequency and the period of this wave.